This section is about oxidation-reduction reactions, and these are a little more important. So in an oxidation-reduction reaction, what we have is electrons being transferred. So one substance is giving electrons to another substance. That's the characteristic of an oxidation-reduction reaction. So oxidation-reduction is a bunch of syllables. It's also called a redox. Re from reduction, well, I guess read from reduction, and ox from oxidation. It looks like redox, which makes me think of Redbox, but that's just totally unrelated. So redox reactions. A lot of redox reactions involve something reacting with oxygen, and that's how oxidation originally got its name, is that something is combining with oxygen, it's being oxidized. So here we see iron reacting with oxygen to form Fe2O3. Octane combusting, burning with oxygen to form carbon dioxide and water. Hydrogen and oxygen combining to form water. Now, when we look at these molecular equations, it's not obvious that any electrons have been transferred. This is an illustration. This balloon is a very dangerous mixture of hydrogen and oxygen, and you tape a candle to the end of a meter stick. Literally, that's what everybody does, because you want to be far away from it. And you light the balloon, and it goes kaboom, right? I mean, it's pretty significant. In that process, the hydrogen and oxygen gases combine to form water. That's a combustion redox reaction. This is a redox reaction that occurs without combustion. Here we have sodium reacting with chlorine to form NaCl. Now, if we look at what's going on here, the sodium doesn't have any charge on it, does it? And the chlorines don't have a charge. But we're making an ionic compound. In the ionic compound, we have sodium ions and chloride ions. So now the chlorides have a -1 charge, the sodium ions have a +1 charge. How did that happen? In the process of the reaction, there was an electron transfer. Sodium gave an electron to a chlorine, and then they became sodium ion and chloride ion, and then they thought they were super attractive, and they stuck together and made sodium chloride. Reactions of metals with nonmetals are going to be redox reactions. And so here we can look at sodium reacting with oxygen, right? So that would be, well, nothing. That would just be what it is. And sodium reacting with chlorine. This one's, you've got oxygen involved. This one's, you've got chlorine. But both metal, non-metal. Both of these involve converting free elements into ions. So the sodium becomes sodium plus, the oxygen becomes O2 minus, and we just talked about what happens with the sodium chloride. And when you look at this right here, you can see why we don't put the charges in the formula for an ionic compound. Right? It gets pretty messy. So in order for a free element to become an ion, it has to gain or lose electrons. So the thing about electrons is there's no homeless shelter, there's no lost and found for electrons. So if you want to get rid of an electron, you actually have to give it to another atom. If you want an electron, you don't go to the bank and withdraw electrons, you have to get it from another atom. So in oxidation reduction, one atom is losing an electron, another atom is gaining an electron. It happens together. So what we're seeing here is that the sodium, to become an Na+, an ion, loses an electron. And the chlorine gains an electron. It looks like it's 2 electrons, but it's 2 chlorine atoms, and it makes 2 chloride ions. So losing an electron is oxidation, and gaining electrons is reduction. So oxidation is loss of electrons, reduction is gain of electrons, oil rig. Oil, oxidation is loss, rig, reduction is gain of electrons. And unless you do these sorts of things all the time, I mean, I teach this stuff every semester, right? And I'm still thinking oil rig in my head every time I need to identify an oxidation or a reduction, because it's just too easy to get confused, right? So to make things a little more interesting, the transfer of electrons does not have to be a complete transfer, as in, completely transferring an electron from one to another, forming ions. We can just have a partial transfer, meaning you went from equal sharing of electrons to now it's unequal sharing of electrons. So the reaction of hydrogen and chlorine is going to make this is a gas, it's hydrogen monochloride. So here we have the hydrogens sharing a pair of electrons, and here we have the chlorines sharing a pair of electrons, and we see that these molecules are symmetrical, right? There's not one end that's red and one end that's blue. When hydrogen and chlorine form a covalent bond, chlorine hogs the electrons. We'll explain why later. But chlorine has increased electron density, and the hydrogen has decreased electron density. You could think of this red thing here as being like a blanket, and you're sleeping with your sibling in a double bed, right? And there's one blanket. And what happens? Somebody hogs the blanket, right? Or there's an outright fight. And this is how it ends up. The stronger person ends up with the blanket, and this one is kind of out in the cold. And look, he's blue. He's turning blue. So we don't have charges, plus and minus, but we have partial charges. There's our D with a posture problem. So this end is partially positive, that's partially negative. Electron transfer has occurred, but it's just part way. It's not all the way. Okay? So the chlorine has increased its electron density. It has gained electrons. The decrease in electron density comes for hydrogen. And so then, we think oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Chlorine gained blanket, right? Gained electrons, gained more of the electrons, and so that's being reduced, and the hydrogen is being oxidized. Okay? So when we look at nonmetals, it's much harder to identify a redox reaction. We don't see, something gaining oxygen, as in combustion, and we don't see ions being formed. So chemists made up something called oxidation states to help us figure out what's being oxidized, what's being reduced. Basically tracking the electrons. And it takes a little bit of getting used to, but it's actually much easier than learning all the theory behind being able to predict this otherwise. So it's important to remember that oxidation states are not ion charges. They are imaginary charges, whereas ion charges are real, measurable charges. And the reason I'm telling you this is because the oxidation state and the charge that an element takes when it becomes an ion is often the same. And so it can be really easy to mix them up. but oxidation states are just imaginary. So we have a set of rules, and again, the rules make it look much harder than it is. Free elements have an oxidation state of 0. Monatomic ions have an oxidation state equal to their charge. So here, calcium has a +2 oxidation state because it has a 2+ charge. Chlorine has a -1 oxidation state because it has a -1 charge. And that's why it can be easy to get them mixed up. But it also makes them easy to assign. If you've got ions, the charge is the oxidation state. As with actual charges in ionic compounds, the sum of all the oxidation states, if you have a neutral compound, the oxidation states have to add up to 0. And if you have an ion, like nitrate ion, then the oxidation states of the nitrogen and the 3 oxygens are going to add up to -1. In their compounds, metals have positive oxidation states equal to their ion charge. And I don't understand why they make this a separate rule, because metals are monatomic ions and they have an oxidation state equal to their charge, right? So here sodium's +1 and calcium's +2. So far it's very much like ion charges. The tricky part is when you have nonmetals, like H2O. Well, you don't have ions, so how do you decide what the oxidation states are? We're going to use this table. Okay, so we've got fluorine, hydrogen, oxygen, 7, 6, 5. And what this is like a list of who gets first choice. All of the nonmetals in Mrs. K's chemistry land want to have an oxidation state that's equal to the charge they would have if they were an ion. Like, I'm not actually an ion, but if I was, this would be my charge, and so that's what I want my oxidation state to be. So fluorine would be -1, hydrogen would be +1, oxygen would be -2. Oxygen as an ion is a -2, right? Group 7 is -1. All the group 7 elements, the halogens, they make -1 ions. Group 6 is -2, group 5 is -3. Okay? So the hard thing is remembering how the table works. The oxidation state is the same as the charge that element would have as an ion. So we don't really have to do anything for that, but this order we have to do something about. Pho. You know what pho is? Really good noodles, right? Except it's with a P. Close enough. It's an F sound, right? Pho 765. There's actually a restaurant that's Pho 76. Just gonna convince them to add a 5, and then there'll be oxidation state crib notes. Pho 765. Do you think you can remember that? Pho 765. So when we have nonmetals, we're going to go through this Pho 765. Is there fluorine? If there is, he gets to choose. Well, she gets to choose. Is there a hydrogen? Is there an oxygen? Is there group 7, group 6, group 5? That's the order in which they get to choose what they want. You can have fractional oxidation states. I don't think we run into any of them in Chem 1A, but they can be fractional because we're not actually talking about transferring a whole electron. And just so you know why the numbers are showing up like this, we write the sign before the number for an oxidation state and after the number for an ionic charge. And I don't expect you to remember that. Okay, let's practice a little bit here. Assign oxidation state to each atom. So each atom has an oxidation state. So like in this compound here, where we have 3 atoms, each atom has its own oxidation state. So what's the oxidation state for Cr? That would be 0. This is an element, right? It's not an ion or anything. What's the charge on the element? 0. What's the oxidation state? 0. What about this chromium ion? Yeah, it's got a +3 oxidation state because it has a 3+ charge. Here we have CCl4. This is carbon tetrachloride. That's not 2 carbons and 4 iodines. So we've got carbon and we've got chlorine, 2 nonmetals. Fe765. Is there fluorine? Nope. Hydrogen? Nope. Oxygen? Nope. Group 7? Yes. Chlorine is group 7. What would group 7 take as a charge for an ion? -1. So the chlorine has a -1 oxidation state. There's 4 of them. And then there's carbon. So this is a neutral compound, which means that the oxidation states have to add up to 0. So each of these chlorines is -1, and there's 4 of them. What's the oxidation state for the carbon? +4. It acts a lot like charges on ions, which is both good and confusing. Any questions about that one? SRBr2. Do we have a metal in there? Yeah. So the metal's an ion. What's the charge on the strontium ion? +2. So strontium is going to have a +2 oxidation state. The strontium is +2. There's 2 bromines. What are they going to be? -1. And just like their charges, the oxidation states add to 0. SO3. That's another one where we've got just nonmetals. Fe765. Fluorine, nope. Hydrogen, nope. Oxygen. So oxygen picks. Oxygen picks what it would have as a charge for an ion. -2. There's 3 of those. There's 1 sulfur. Sulfur just has to make up the difference. So what's sulfur going to be? +6. Here we've got the nitrate ion. So nitrogen and oxygen, Fe765. No fluorine, no hydrogen, oxygen again, right? And oxygen is still going to pick the -2, and here there's also 3 of them. So together, that's -6. Is this a neutral compound? No, it's got a -1 charge. So the oxidation states have to add up to the charge, -1. So nitrogen needs to be +5. Make a little bit of sense? So to identify redox reactions, there has to be an oxidation and a reduction. And sometimes you can see this pretty easily, other times you can't. it's when you've just got nonmetals that it gets a little tricky. So here we've got carbon reacting with sulfur, and it's making carbon disulfide. So we need to look at the oxidation states. This is carbon, the element, it has oxidation state of 0. Sulfur, the element, 0. In CS2, Fa765, no F, no H, no O, no 7, but 6, group 6. Sulfur is in group 6. So it gets to pick, it picks -2. So each of these sulfurs is -2. That means the carbon has to be +4. And then we're going to look at how did the oxidation states change. Well, carbon went from 0 to +4. That's an increase in the oxidation. Sulfur went from 0 to -2. That's a reduction, a decrease in oxidation state. The reduction, decrease. If the oxidation number goes down, if it is reduced, that thing is getting reduced. If the oxidation state goes up, it's an oxidation. That does not contradict when we're talking about loss of electrons or gain of electrons. Because in order to get an increase in your oxidation state, you have to lose electrons. And to have a decrease, you have to gain electrons. So oxidation is still loss, reduction is gain. Just another way to think about it. Use oxidation states to identify the element that's oxidized and the element that's reduced in the following redox reaction. So when we're looking at redox reactions and we're talking about what's oxidized and reduced, we're talking about an individual element, not a whole compound. So what we have to do here is identify the oxidation states. So here's tin. What's that? 0. Right? Here we have HNO3. All right. Fa765. No fluorine. Hydrogen gets to be what? +1. And then next is oxygen. Oxygen gets to be -2. There's 3 of those. Sometimes it helps to draw them all out. What's the nitrogen then? It's got to be plus something so that all of these numbers add up to 5. I'm sorry. It is 5. Essentially, we're asking ourselves 1 plus x -2 -2 -2 equals 0. What is x? X is 5. Okay, over here, SNO2. How do we figure that one out? Well, that one actually has ions, right? What is the charge on that tin ion? +4. Because there's 2 oxide ions, and each of those has an actual charge of -2. These oxygens didn't have a -2 charge. They had a -2 oxidation state, which is sort of like a make-believe charge. Here we have NO2. Again, 2 nonmetals, Fa765. So who gets first pick? Oxygen. And oxygen always chooses -2. There's 2 of them. So what's the nitrogen? +4. And then over here we've got H2O, Fa765. Hydrogen gets to pick. Hydrogen picks +1. And oxygen has to be -2, which is actually what it would pick. And so it's pretty happy here. So we're supposed to identify the element that's oxidized and the element that's reduced. What we're looking for is something whose oxidation state changes. Like if we look at the hydrogen, it was +1 here, and it's +1 there. That didn't change. Oh, I didn't really want to do that. Just cross that guy out. What else didn't change? Oxygen. Oxygen was -2. Oxygen's all over the place over here, but it's still -2. Tin is 0, and over here tin is +4. Is that an increase or a decrease? That's an increase, right? An increase in oxidation state. That's an oxidation. And then we've got nitrogen going from +5 to +4. That's going down. The oxidation state is being reduced because nitrogen is being reduced. So tin is oxidized. Nitrogen is reduced. Any questions? So just to restate it, oxidation reduction have to happen at the same time. If one atom loses electrons, another atom must take them. So we have the reactant that reduces an element is itself oxidized. And the reactant that causes something else to be oxidized is itself reduced. And I don't know about you, but that's just confusing. So let's think about Hollywood and movie stars. So these guys have agents, right? Does the agent star in the movie, or does the movie star in the movie? The movie star, right? What does the agent do? The agent helps them get the job, right? So the reducing agent causes something else to be reduced. The oxidation agent causes something else to be oxidized. So here we're supposed to determine whether or not each reaction is a redox reaction, and for the redox reactions, identify the agents. So there's there's two types of reactions that you can just recognize. A metal reacting with a nonmetal. Because when that happens, you have elements becoming ions, and that involves transfer of electrons. The other one is something reacting with oxygen. That's going to be a redox reaction. So this first one, a metal and a nonmetal, that's going to be an oxidation-reduction reaction. Here, what we're seeing here is a net ionic equation. Are things changing their charges? Aluminum is going from an element to a +3 ion. That involves losing electrons, right? So that's a redox reaction. Here what we have, see this solid here? That's a precipitation reaction. So lead and nitrate, lithium and chloride went to a party in a beaker, and lead and chloride got into a long-term relationship, right? And lithium and nitrate are just hanging out, mingling with everybody else. If we look at the ions that are present here, there is no changing of charges. right? PbNO3, that's lead 2. And this is also lead 2. Here, lithium is +1 and lithium was +1. There's no charges that are changing, so that's not a redox reaction. What about this one? That's something reacting with oxygen, right? Something's getting oxidized. Okay, so we identified which ones are redox reactions. This one, we actually have ions, and the oxidation states are the same as the ion charges. So if we look at those, we have lithium ion and chloride ion. It's going from 0 to +1 and 0 to -1. The oxidation state being reduced means that chlorine is being reduced, right? The agent is the opposite thing. So it's being reduced, it will act as the oxidizing agent. This thing gets reduced, lithium is going up, lithium gets oxidized. It lost an electron, chlorine gained an electron. They happen together, one loses, one gains. So chlorine is being reduced, so chlorine is the oxidizing agent. Lithium is being oxidized, lithium is the reducing agent. The whole agent business is especially not important, but here we have aluminum going from 0 to +3. Is that oxidation or reduction? It's oxidation. Oxidation is loss of electrons. To go from 0 to plus, you have to lose electrons. Here the tin is going from a +2 to a 0. The oxidation state is going down, it's being reduced, that's the reduction. So tin, and we don't want to say the tin atom because that's the product. We need the reactant. The tin 2+ ion is being reduced, so it's the oxidizing agent. The aluminum is being oxidized. That's the important thing to be able to figure out. And so that makes it the reducing agent. It's not confusing at all. Okay, this one down here, we need to use oxidation states because we have two nonmetals, Fe765. So oxygen gets to choose, and oxygen chooses -2. There's 2 of them. Carbon has to be +4. So which of these, carbon or oxygen, is being oxidized? Carbon is being oxidized. What kind of an agent is it then? A reducing agent. Oxygen is the oxidizing agent because oxygen is causing the other guy to be oxidized. Please accept my sincere apologies. The activity series. So, redox reactions do not always happen spontaneously. If we put a magnesium strip into a solution of copper, this oxidation-reduction reaction is spontaneous, and we end up with copper metal being dissolved on the zinc and zinc going into the solution. Notice how the solution is less blue here? The blue color is from the copper ions. So copper ions are leaving the solution and turning into this kind of looks like black stuff, right? The reason this happens is that magnesium has a greater tendency to lose electrons than copper does. Okay, so this works out into the going to a party thing. This is a net ionic equation, right? There has to be an anion in there. Let's say it's chlorine. So we've got magnesium plus, that would be copper chloride, goes to magnesium chloride, plus copper. We do the total ionic equation and the net ionic equation, we get this. So here we have copper, a guy, with chlorine, the girl. And yeah, I haven't figured out what to do with, he had two girls, or just one. One element. So copper and chlorine are going to the party. Who is magnesium going with? Nobody. Do they still call that going stag? Yeah. He's going by himself, right? So what happens at the party? Magnesium now has chlorine. And copper goes home by himself. Aww. Why did chlorine leave copper and go to magnesium? He was more attractive. He was more attractive in some way. We don't know exactly, but obviously more desirable. Okay? So that desirability is related to a tendency to lose electrons. Magnesium has a greater tendency to lose electrons, so magnesium will take copper's girl. Okay? What if we have the opposite and we have magnesium going to the party? So here we see magnesium 2+, and you're like, well, that doesn't look like magnesium has a girl. Magnesium has a charge. Magnesium is charged up because he has a date. She's just not with him yet. So the guy with the charge, that's the one that's got the girl. Okay? So magnesium goes to the party with the girl. Copper goes stag. What happens? There's no chemical reaction. The copper strip stays the same, the magnesium stays in solution, because magnesium is still more desirable than copper. So magnesium goes home with the girl, and copper goes home alone. Okay? So to be able to predict this, we have what's called an activity series of metals. This lists the metals in order of decreasing tendency to lose electrons. So if we think of this taking the girl thing, this is a list of who is coolest or most attractive, right? I think some girls in high school actually had lists. You know, they ranked the boys. It's not nice, but anyway. So if you are comparing two metals and you want to see which one is going to leave with the girl, is going to have the charge, the one who's higher up on the list is going to win. So each of these reactions would be a half reaction. Let's just go to this list. So what we're showing in the list here, lithium is losing electrons, right? Oxidation is loss of electrons. And I suppose this is a new twist to this. I suppose, maybe one of the appeals of lithium is if you think of the electron as money or gifts, lithium is more likely to give you electrons, to give you presents, right? So that might increase his desirability. I don't know. So lithium is the coolest guy, right? And gold down here, gold is just a big old nerd, right? So we could predict what's going to happen. Let's say we have chromium 3+, and calcium. So chromium has the girl, calcium doesn't. Who's going to leave with the girl? Calcium, because calcium's higher on the list. Calcium's up here, chromium's down here. So to show that calcium has the girl, we're going to write calcium 2+. And then the chromium's going to be 0. Does that make sense? So which metal is most easily oxidized? I'll let you look at the list. Which metal is the coolest? Sodium. So sodium is most easily oxidized. Gold is not easily oxidized, which makes it really good for jewelry because it doesn't tarnish. It doesn't react with much of anything. So determine whether each redox reaction is spontaneous. No, I didn't put it on there. Okay. So here we have, the good news is this is the last slide. Here we have zinc and nickel. So zinc and Ni2+. Who has the girl? Zinc or nickel? Right here. Nickel does. All charged up because he's got the girl, right? He's got a 2+ charge. He's happy. This guy's neutral, right? So what we need to find out from that activity series is which of these is more desirable, which one's higher on the list. So if we look at the list, here is zinc, and here's nickel. So that tells me that zinc is going to leave with the girl. If zinc came with the girl, he's still going to leave with the girl. But did zinc come with the girl? No. That means that zinc is going to leave with the girl, he's going to have the charge, and nickel's going to go home alone, right? So we say this is a spontaneous reaction. That's going to happen. If we had the reverse situation, where zinc went to the party with a girl, and nickel didn't have a girl, zinc is still cooler than nickel. And so the girl's going to go home with the guy she came with because he was the coolest one. What about this one? Zinc and calcium. Who's got the girl to start with? Calcium, because he's charged up, right? So we need to look at our list and find copper and zinc. Copper's much below. It would be calcium. Copper is below, but we're not talking about that. Thank you. Silly teacher. Here's calcium, and here's zinc. So which is more desirable? Which is more likely to lose electrons? Calcium. So that tells me calcium is going to go home with the girl. And in this situation, calcium came with the girl. So is zinc going to steal the girl and leave calcium alone? No, can't do that. So that's not going to happen. We say this is non-spontaneous. Any questions? You can imagine all the things that happen in Mrs. K's chemistry lab.